servant who works in the ISRU group within the Propulsion and Power Division at the Johnson Space Center. His work in the field of ISRU includes the development of multiple systems at varying scales with applications to both the Moon and Mars. He has been granted innovator status for multiple inventions submitted to JSCS Technology Transfer Office. Aaron is a member of AIAA and Mensa. With great pleasure, we invite Aaron Bass to take the floor.
Well, first off, thank you so much for inviting me here. It's a great honor to be here and a pleasure to talk to you today about in situ resource utilization. This is a field of study that I've been developing technology for since about 2005, and happy to share this experience with you today. So you heard a little bit about ISRU this morning from the first presentation, so I'm glad Carlos was able to give that presentation in Spanish. It'll be easier to follow mine, I think. So I'll cover some of the same topics, but I'll go over in a little bit more detail about what NASA is doing specifically and some of the missions related to ISRU. So ISRU is a very broad field. I enjoy working here in this field because every day is different than the next. We do ISRU on Earth, but we just call it engineering. Everything comes from a resource somewhere here. And on the Moon and Mars, we'll do the same. There's just a little bit less to work with, but there's still quite a lot that's very useful. So to cover the whole topic of ISRU would take much more than an hour. There's actually whole conferences dedicated to this subject. But today I'll mostly talk about the Moon and Mars, since those are the most active areas. So several resources on the Moon. Primarily we have oxygen, the lunar regolith, that's the technical term for it. Lunar soil is also acceptable if you're talking about the fine material. It has about 45% oxygen, so there's a lot of ways to get that oxygen. We also have water ice, talk more about that. There's metals, metalloids. The regolith itself can be used for construction. Solar, wind, and planted volatiles, and of course abundant energy. Mars has oxygen in the atmosphere. We'll talk a little bit about that. Also, there's water all over Mars. And of course, there's also metals and regolith and other things. So we'll just jump into the details here, starting off with the Moon. So you've probably heard about water on the Moon. One thing interesting you should know is that there's actually no dark side of the Moon. This is it's a term that gets thrown around. I hear it even at conferences and in the news, but the Dark Side of the Moon is just a Pink Floyd album. It's a good album, but it doesn't exist in real life. We have the near side that always faces Earth. We have the far side that always faces away from Earth, but they have equal sunlight. There are areas, though, that actually are dark on the poles of the Moon. So there's craters at the poles that have never seen sunlight for billions of years, and those craters are cold enough to pull in water ice and keep it there. And so we've actually been able to observe this through multiple missions, starting with in the 90s, we had the Clementine mission was the first to get that indication, followed by Lunar Prospector. And then the Chandrayaan mission also had an instrument on it that was able to detect the water ice. Our best confirmation came in 2009 with the Lunar Reconnaissance Orbiter and LCROSS mission. So I'll play a quick video on the next slide that actually talks a little bit about the Lunar Reconnaissance Orbiter. And this will tell you, I think there was actually a question asked in a previous presentation about how we know that the water is there, how we sensed it. So this next video will go into a little bit of detail about how we did that. Actually, it's the next slide. So this is, before I get to that video, in addition to the Lunar Reconnaissance Orbiter, in parallel with that mission, there was the LCROSS mission, which somebody had the crazy idea of taking an upper stage of a rocket and crashing it into one of these permanently shadowed regions, and then analyzing the plume to actually confirm that there was water. So they did that. This is the only data point that we have right now that shows what the actual concentration of water ice is in these regions, and also gives us an indication of what else is mixed in with the water. There's some other useful volatiles that are mixed in. Again, I think this next slide here is about the LRO, and there's a little bit about the L-Cross mission as well.
Since the 1960s, scientists have suspected that frozen water could survive in permanently shadowed craters at the moon's poles. Both hydrogen and oxygen could be trapped within the lunar soil. So to find water on the moon, scientists are looking for indications of hydrogen using the Lunar Reconnaissance Orbiter's LEND neutron detector. By observing the interaction of neutrons with the lunar soil, scientists can interpret how much hydrogen is likely to be present. In order to make a detailed interpretation, however, LEND needs to observe a large number of neutrons. Because LRO is constantly moving, LEND is never over one place long enough to count many neutrons. So, to make a detailed interpretation of neutron flux, scientists add together many measurements from many orbits. With each orbit, LEND's dataset gets larger, and its picture of neutron flux continually improves over time. The dark blue regions in this visualization are places on the south pole of the moon with a suppressed flux of neutrons because of their interaction with hydrogen. These areas strongly suggest the presence of water frozen within the soil. While previous lunar missions have observed indications of hydrogen at the moon's south pole, the LEND measurements for the first time pinpoint where hydrogen, and thus water, is likely to exist. By combining years of LEND data, scientists see accumulating evidence that there is water on the moon. And as LRO continues to return data, our picture of the moon and its water will continue to get better in the years ahead.
Okay. Credit to Goddard for that video and for that mission. Yeah, so why is this important? I mean, obviously, humans need water, right? We can only survive for a few days without it. But more significantly, we can turn it into rocket propellant. So this is really game-changing, or at least I think this is what will enable people to actually live on the moon and Mars, is when we can produce our own rocket propellant, because it's just very expensive to put mass on the moon and Mars. And so if you just look at today's vehicles that are designed to land on Mars, there's a Blue Origin lander, there's a Starship. Fortunately, both of those companies have embraced ISRU and are using liquid oxygen as their propellant system, rather than the types of fuels we use in Apollo, which we wouldn't be able to make from the resources there. But if you look at how much propellant they take, roughly 10,000 kilograms, and the cost of landing 1 kilogram of mass on the lunar surface right now is about $1 million. So we're talking billions of dollars just to land the fuel that you need to get off the planet. So if we're going to live there, being able to produce our own propellant is going to be very important. It's going to make the cost actually enabling. And so water can be split into hydrogen and oxygen using water electrolysis. You basically just run an electric current through it, and this technology is pretty well understood. And once you have hydrogen and oxygen, you can liquefy it, turn it into rocket propellant. And it's not just any rocket propellant, it's actually the propellant of choice for really heavy vehicles. So the Saturn V, the space shuttle, our current space launch system, all of those use liquid oxygen and liquid hydrogen as their propellants. Very high performing propellant combination. So it's very fortunate. And where we have water, as long as we have power, we can make our own rocket fuel to leave the moon and Mars. So I believe this next clip is our current NASA administrator just emphasizing the importance of this.
Is there any scientific goal to going back to the moon?
There is water on the moon. We want to get there and learn how to harvest that water, turning that water into hydrogen and oxygen, and that will give us the fuels to explore the heavens.
Yeah, so I love that video clip. I snagged it from the news when I saw it, and like to share that because it is important, not just for living on the moon and Mars, but also for getting further out, because if we can produce propellant there, we can essentially turn the moon and the Mars into a gas station for the further reaches of the solar system, where we can start mining asteroids, where we can start really expanding our economic sphere into the solar system. So we have a long ways to go. Right now, we only have the one data point from LCROSS, what I mentioned before, in terms of what the concentration of water is on the moon. It's roughly 5% per the LCROSS data. That's not enough data to build a full ice mining operation. We need to get more. So NASA does have some missions coming up very soon. The first one is called Prime 1. This will be a drill and a mass spectrometer on a static CLIPS lander. So they'll actually drill into the surface of the moon in an area where they think there could be some subsurface water ice. And as the water sublimes into space, which it will do as soon as it's heated above 150 Kelvin, which is not very warm at all, so pretty easy to get that to turn into a vapor, then we'll be able to sense how much is there and get some idea. So next video is just an overview of this first mission that will hopefully be launching in a few months within December of this year.
NASA's Artemis missions will establish the first long-term human presence on the lunar surface. Living and working on the lunar surface will require using resources that are already present there, like water ice, which can be used for life support and fuel. The Polar Resources Ice Mining Experiment 1, or Prime 1, will be deployed to the lunar South Pole by our commercial lunar lander partner, Intuitive Machines. Prime 1 is intended to drill for water on the lunar surface. Prime 1 is the combination of two instruments, a drill built by Honeybee Robotics called Trident, which stands for the Regolith Ice Drill for Exploring New Terrain, and the Mass Spectrometer Observing Lunar Operations, or MSOLO, which is a commercially available mass spectrometer from our industry partner Inficon that we have modified for operation in the harsh space environment. Trident will drill into the lunar surface, taking one small bite deeper into the soil at a time and bringing that sample up and depositing it on the lunar surface. MSOLO will then evaluate those samples as they arrive on the surface to identify and measure the composition of water and other volatiles emanating from the samples. The objective of Prime 1 is to inform NASA's plans for mining resources on the lunar surface, as well as mission operations for a future NASA lunar rover mission called Viper. So how will we extract water on the moon? The Prime 1 mission will set the foundation for future resource utilization on the moon, a key component for the success of upcoming Artemis missions, as well as expanding human exploration of our solar system.
Okay, so hopefully we'll get some more data very soon with the Prime mission. But again, that will just be one data point because it's a static lander. So they'll get some information about water ice wherever they land. They may get a few data points, but it'll just be in one location. Mostly, Prime is a technology demonstration where they're going to be testing the drill and the mass spectrometer that will be used later on for another mission following up about a year later called Viper. And Viper will have the same instrument suite. It'll have a drill. It'll have a mass spectrometer that can determine not just water, but anything else that's below the surface. But that'll be in a rover. So we'll be able to get a lot more data with the Viper mission. This has been a long time. It's been in work since probably 2010. Finally, hopefully, we'll be flying within a year. And so there's a quick video on the Viper mission as well.
The future of human space exploration is being driven by what we can discover and accomplish on the moon. And with NASA's confirmation of ice existing at the lunar South Pole, the critical task of finding and mapping where water exists, what form it is in, and where it came from can now begin. Leading us on that journey will be NASA's first mobile robotic mission on the moon, known as Viper, the Volatiles Investigating Polar Exploration Rover. It will be delivered to the Nobile region of the South Pole as part of NASA's Commercial Lunar Payload Services Initiative. This region sits just outside the western rim of Nobile crater and covers an area of 36 square miles. As the first ever resource mapping mission on the surface of another celestial body, Viper will roam the surface equipped with 3 science instruments and a drill to detect and analyze various lunar soil environments at a range of depths and temperatures. The rover will venture into permanently shadowed craters, some of the coldest spots in the solar system, where ice reserves have been preserved for billions of years. NASA had 4 critical parameters when choosing a landing site for Viper: available sunlight, Earth visibility for communications from the Moon to the Earth, data showing the potential presence of water and other resources, and terrain that is well suited for Viper to navigate. The area to the west of Nobile crater met these conditions. Once on the surface, Viper's mission will last 100 days and cover between 10 to 15 miles. And while a baseline traverse route through the Nobile region has been identified for the rover, the scientific discoveries Viper makes along the way will actually influence where the mission team sends it next, so its planned route will most likely change. During its travels, Viper will visit at least 6 locations where data suggests ice could be found. By helping determine the locations of where water and other resources exist, Viper's findings will help pave the way for future landing sites under NASA's Artemis program. The prospects of achieving a long-term human presence on our moon never looked so bright.
So very much looking forward to the Viper mission. We'll be getting a lot more data very soon on the water ice at the poles. I should mention that there are other space agencies with similar missions. I know JAXA has one very similar to Viper. There's others that are in work. And this is just the beginning. You know, the Viper is going to give us a lot more data, but both Prime and Viper are somewhat limited in that they won't make an attempt to actually contain the water. They're basically going to drill a hole and let that escape to space in order to try to get a rough idea of whether it's there or not. So we'll need to have more prospecting missions in the future before we can actually start really mining water ice at a useful scale. Some of those future prospecting missions, there's an instrument here that I'll talk about because this was actually something that I worked on personally. This is a project I've been developing for the past few years, which will be, it's designed for future prospecting missions, but the difference is this will actually capture the water and try to contain it, which is something we'll need to do eventually if we want to utilize water. So this one doesn't have any voice, so I can just kind of talk through this video and describe what you're looking at. So in this case, we would take a drill similar to Viper, but this time we would put it in a small container. And with that small container, as long as you do the transfer cold enough, shouldn't lose any water. And we've done thermal analysis to show that we can do this. But then we can take that container and first weigh it so that we understand the mass of the sample, so we can get a good, highly accurate concentration of water in the sample. We'll have a dust cap in place so that prevents any of the regolith from escaping due to other volatiles that may be coming out. We'll weigh the sample and then we can seal it. And once we seal it, then we can actually control the heating of it. So we can drive off water and other gases in a controlled way to determine exactly what temperatures those will be driven off, and also quantify to a high accuracy. But in addition, we can capture the water. So this is a little water droplet demo. So in theory, with this type of prospecting device, we'd be able to actually return water samples to Earth for further analysis. Sorry, the music was a little loud. I probably should have cut that part out. But yeah, so with this type of prospecting, we can actually return lunar water. And this is what we'll have to do at a larger scale if we want to actually start using the water ice. So hopefully in Viper 2 or 3, we'll have something like that. Now, that whole prospecting campaign will need to play out before we can actually start mining ice at a useful scale. But we can start developing the technology now. And so we've already been thinking of ways that we can extract water ice and utilize it at a large scale. So this concept was presented at I think an ADI-AA conference back in 2020. This was what we call our pilot plant scales. It's designed to extract or produce about 1,000 kilograms of oxygen per year from lunar water. The basic components are an excavator, an auger system that you can use to heat the icy regolith, and then a condenser that can truck the water back out of the crater. So I can go into a little bit more detail about some of those different pieces that are in various stages of development. The first part is the excavator, and so this is being developed at Kennedy Space Center. They call it the Razor. So they've shown that it's done a pretty good job of being able to scoop up icy regolith. But there's actually a lot of private companies that are developing this type of technology. This is an area where universities have been getting involved as well. I think it's going to take a lot of these type of excavators to actually get the amount of material we need to make useful quantities of propellant on the moon, and Mars as well. So that you could see the football field on the right. The blue part is roughly how much material you would need to excavate to refuel a rocket that can actually produce enough propellant to launch from the moon with a crew of about 4 people. So that's about as much material we need to be excavating to actually not have to bring all of our propellant with us. So it'll take a suite of vehicles to do that. This next part is what we do with the regolith once the excavators deliver it to the plant. So this is some technology we've been developing at Johnson Space Center. It's fairly simple. You would just pour the icy regolith into the system where it can be sealed in a pressurized chamber. We have an auger that moves it along a horizontal tube where we can heat it and release all of the water ice, or it basically vaporize it, and then feed that into a condenser where we can trap it. So this has been working pretty well. It's pretty straightforward. This particular design is much bigger than anything we would put on the moon, but we use this as a test apparatus. It's used commercially for drying powders and worked pretty well for this application. Okay, so then the next part, it's a little bit trickier, is actually purifying the water. So if we want to actually turn this into rocket fuel, the technology exists to do that. Water electrolysis has been used on the space station to convert water into oxygen for the astronauts to breathe for decades. But that type of technology that's used on the space station is called a proton exchange membrane, requires water to be ultra pure and deionized. Basically, it can't be conducting an electric current because with this process, you have to control where the current is in order to make sure you're not electrifying your whole system that has oxygen and hydrogen in it. It's a bad combination. So ultra pure deionized water is important. It's also important for the health of the device that we call the electrolysis stack from getting poisoned. But getting to that point is pretty difficult. The only way that we really do that terrestrially is with deionizing resins. And so on the moon, we won't have that. You can't just take a tank of purifying resin that you have to refill every so often. So we've been looking at ways to purify water without deionizing resin, and we've gotten pretty close. On the left side of the chart is some data we've been collecting to see how much the actual particulate, the grains of lunar dust that make their way into the water, even past a filter, still applies some level of conductivity to the water that we have to deal with. So we have that data now to understand contamination contribution from the dust. On the right, there's other volatiles that are mixed in with the water that have to be separated. There's things like H2S, CO2, ammonia. And so a company called Paragon Space Development has been developing technology to separate water from those other gases, and they've collected some data on as well. So we're getting closer to being able to get the water to levels that we need to be able to split it into hydrogen and oxygen. But there's also different technology that doesn't require ultra-pure water. So another more advanced form of electrolysis is something called a solid oxide electrolyzer. And this is technology that hasn't been around as long. It's actually been demonstrated on Mars. But this would actually convert steam into hydrogen and oxygen. So it doesn't require the same level of purity. So we think this might be a good approach where we can actually do this process without any kind of consumables required. And this is a rough block diagram schematic of how that might work. This is actually something I'm working on now that we hope to build and demonstrate by the end of next year, which is where we'll take a contaminated source of water and just put it in a pressure vessel and heat it up. And we'll go through 2 levels of purification. So one loop will go through something called a Nafion membrane that is very selective to water. So it's the first purification step. Then we'll send that steam directly to a solid oxide. Yeah. So dirty water starts off here, recycle through a Nafion membrane. Pure water comes through here, and then we recycle through solid oxide electrolyzer, which then will produce pure dry oxygen and humid hydrogen, but we can dry the hydrogen, and then that's basically all the steps you would need to go from contaminated source of water to rocket propellant. So we're hoping to demonstrate this next year. Hopefully have some good data by then. Now, one of the big challenges, so as an engineer, we always look for, what are the challenges? What hasn't been done before? What could use improvement? I think one of the biggest areas in ISRU is hydrogen liquefaction. This is an area that could still use some improvement. It's just very difficult to pull heat out of something that's already very cold. Liquid hydrogen is 20 degrees Kelvin. It's one of the coldest substances there is. It's hard to deal with. I mean, we use it as rocket propellant on the shuttle, but when we do that, we load those rockets very quickly and then launch them. They're not sitting there stored full of liquid hydrogen because it would boil off too quickly. So that'll be a challenge if we're trying to actually make this on the lunar surface. With the current cryo-cooler technology, with the state of the art, which is actually a great improvement over what existed even just a few years ago, the amount of hardware we would have to bring to liquefy hydrogen actually would weigh more than the hydrogen. So that's still a challenge. But I'll circle back to that point at the end of the presentation. So aside from water, there's other resources on the moon. I mentioned in the beginning that there's oxygen. I think you heard that today. There's roughly 45% oxygen almost anywhere on the moon. It's bound up in different minerals. So when we see the moon, we see 2 different areas. There's the dark areas, or what we call mare, and then the lighter areas, or what we call the highlands. The chemistry is slightly different. Mostly the dark areas have a little bit more iron. So that is a different resource that we could go after. But we believe that at the poles where we're going for Artemis, it's more like the highlands, so there's not as much iron there. But if we were to do, expand to the darker areas, iron would be another resource that we could go after as well. There's also titanium and mostly silicon. And there's a number of ways that we've used to extract oxygen from these different minerals. So one technique that we've demonstrated, this was back in 2008, to show that we could separate oxygen from iron using a process called hydrogen reduction. The image on the left shows, it's a map of the iron concentrations around the moon. So the red areas are higher concentrations of iron. On the right is a video from a field demonstration that we did in 2008, where we actually took in this case it was Hawaiian tephra, which is the local material on Mauna Kea where our field demo was. Chemistry is very similar to lunar regolith, but we heated it up to 900 degrees Celsius and reacted it with hydrogen. We were able to take the oxygen out. And so you could see the video is showing what we poured out. It's still hot. It's glowing red because those are the temperatures we have to heat to have this reaction occur. But we showed that this could be done. Fortunately, it's limited to the areas on the moon that have iron. There's another process that we demonstrated back in 2010. This is called solar carbothermal reduction, where this will work actually anywhere on the moon. The majority of the lunar soil is made out of silicon oxides. This process can actually take the oxygen from the silicon oxides. So in this field demo, we actually used concentrated solar energy to melt regolith, or to melt this local material, the tephra, in a carbothermal reactor, which then produced water, which we split into oxygen, liquefied it, and fired a thruster. So we call this our dust to thrust demonstration, and just to show that all of these steps could work. Unfortunately, all of this work stopped right after this field demo, because this was in support of the Constellation program. So a lot of this technology was put on the shelf, but with Artemis, we've brought it back. Most of the same team that worked on this is now working on the next step, which is to try to get this technology ready for the moon.
Whenever you go exploring, you never bring everything with you. You always kind of live off the land. Even when we go on road trips, right? We buy gas going, as we travel, and we buy food as we travel. Well, when we go exploring, we need to do that same thing. We need to live off the land. We need to live on the lunar surface, and then eventually we need to go onto Mars and be able to live off of that surface.
The main things that we have available on the moon and Mars, primarily we have oxygen. The lunar regolith is about 45% oxygen roughly. There's a lot of ways to get that oxygen out. This is one of the processes that we're testing today, is a well-proven method for extracting oxygen from lunar soil or regolith.
As we go forward, we need to be in a lunar-like environment. And a big chamber like this allows us to get into that lunar-like environment. This test is extracting oxygen from lunar simulant. And what that is going to enable us to do is live off the land on the lunar surface.
So this is our 15-foot dirty thermal vacuum chamber. We use it to simulate the surface of the moon, because on the surface of the moon there is no air. That means that convective heat transfer does not occur, and any hardware that you build, you need to make sure that it can withstand that harsh environment. So here in the chamber right now, you see our industry partner, Sierra Space's built reactor. We use this reactor to melt lunar regolith simulant.
So we have a reactor that was developed by a commercial company, and we are integrating our gas analysis system with that reactor. And so we have a laser that is going to deliver energy to the regolith, melt the regolith, and we're going to extract the oxygen that way. And then we analyze the gas products with an instrument that is actually flight forward. And so we have a mass spectrometer, and that mass spec is going to be delivered to the moon on earlier CLIPS missions. And so we're using that technology, that partnering with industry, to enable us to analyze the gases and have a path forward to flight.
So this will increase what we call the technology readiness level, because we're performing the test in a relevant environment, the vacuum being the relevant environment. So what the vacuum chamber does is make sure that our thermal management approach is working well.
Our gas analysis system is designed to measure the efficiency of oxygen production. So how much oxygen are we really making with this process? So it's really exciting to be part of that ground floor effort to get that technology ready to support our next big exploration push.
This is really the first step in a series of what I think would ideally be a campaign to where we get to the point where we're extracting useful quantities of oxygen on the lunar surface. So this first step lets us know that we can perform the process, at least at a small scale. What we're doing today is something that's it's never been done before, so that's always exciting.
Okay. Yeah, thankfully I didn't jinx that test because of that interview. Everything worked. So it was an exciting test. So this was something that we did. This is one of the main projects that I'm currently working on, and this is something we did back in February of this year, so relatively recent test. But we basically took a 2 kilowatt laser, fired it through a window of a vacuum chamber into a pressurized reactor, melted the regolith, or simulated regolith. And so the video on the right, you can see basically, what it looks like as we're taking the oxygen out. And the results that we got were actually much better than what we did before. I showed a chart about our field demo in 2010. The amount of oxygen we extracted in this test was about 10 times more. So good improvement on and credit goes to Sierra Space for really advancing that technology. But also the fact that we were able to test in a vacuum chamber means that we're closer to being able to put this technology on the lunar surface. So that's the goal. Hopefully, we're expecting an opportunity within the next year to try and propose this as a CLIPS demonstration. And this is what the rest of it will look like. So we tested the reactor. We can't get concentrated solar energy into a vacuum chamber, obviously, so we use a laser to simulate solar energy, but later next year, this is what we're building now, we'll actually have 2 large carbon fiber mirrors that can, and they're configured in a way that they can be deployed and stowed for launch, deployed on the lunar surface, and we'll actually take the concentrated solar energy and deliver that directly into the reactor. And you can kind of see a sense of scale here with the person, how, what this demo might look like. So we're hoping to have this demonstration go to the lunar surface sometime in 2024. I'm sorry, a proposal would be in 2024, mission probably 27, 28 time frame. But as I mentioned, there's a lot of different ways to get oxygen from regolith. This is one of them. There's a few other technologies, molten regolith, I'll mention some of those as well. But this one does have some advantages that I'll talk about later. So some of the other methods that have been, there's actually about 20 different ways that people have proved to get oxygen from regolith, at least at a small scale in the lab. There's only a handful of those processes that have gotten to the point where you can do a full-scale automated process. But some of the other ones that are promising is molten regolith electrolysis. This is something that there's multiple companies working on this right now. A company in Israel was mentioned this morning. Blue Origin is heavily investing in this technology. And since a lot of that is kind of proprietary, I'm just giving the link to their website if you want to learn more about what they're up to. Vacuum pyrolysis is another method that's been pretty well proven, hasn't exactly been automated, but you can get, that process gets the most oxygen out of any of the other ones, but you have to heat to 3,000 C, so it's not as efficient. So there's just a lot of things to consider. It's there's the chemistry aspect, but there's also how to automate this and how to scale it up. So hopefully we'll have at least 1 or 2 ways to get this working in the near future. Okay, so now I'll move on to Mars. I think it's still, yeah. So Mars has a different set of resources. Mars has an atmosphere, and it's mostly CO2. You may have heard of the MOXIE experiment, which was on the Mars 2020 rover. So MOXIE was a dedicated ISRU experiment that's developed by MIT and JPL. Basically, they're using a solid oxide electrolyzer that I mentioned before, but in this case, they're using it to turn carbon dioxide into oxygen. And so this has actually been demonstrated. They've run it successfully on Mars a few times now and made oxygen at a small scale. So we can scale that technology up. First, so this is a quick video about the MOXIE experiment on the Mars 2020 rover.
Yes, Mars has oxygen, but not very much, and definitely not enough for you to just go out and breathe on the surface of Mars. The density of the oxygen on Mars is about 1/10,000th of what we have here on Earth. But Mars' atmosphere does have a lot of carbon dioxide, about 500 times more CO2 than oxygen. So if we want to harvest oxygen on Mars for use by future explorers or launch systems, a better way might be to pull some of it out of the CO2 and use that instead. So that's where MOXIE comes in. MOXIE is a technology on NASA's Perseverance rover, and it is proven for the very first time that we can extract oxygen from the carbon dioxide in the Martian atmosphere. It's a tech demo, so it only produces a small amount of oxygen, but for future human exploration, we would need to send a scaled-up version, maybe 200 times larger than the current MOXIE. So if such a system were landed on Mars, some of this would provide oxygen for the astronauts to breathe, but most of it would be used as rocket propellant to get astronauts off the surface of Mars and back to Earth. So is there oxygen on Mars? Not much, but that's okay because we can make it ourselves.
So very successful demonstration, and they're still collecting data with MOXIE. Now, in addition to the CO2 atmosphere, there's also water pretty much everywhere on Mars. It's in a different form. It's pretty much just mixed in with the Martian regolith. But this is an image taken from Mars Reconnaissance Orbiter that shows a map of the water concentrations of Mars. And so almost anywhere you go, you can scoop up some regolith and put it in a pressure vessel, heat it up, and get some water out of it. In addition, there's actually large chunks of subsurface ice that is just pure ice. This was an image that was taken a few years ago, also from the Mars Reconnaissance Orbiter. And this is actually an image where a cliff kind of fell off and just exposed this face. It's color enhanced, but the blue is just as pure water ice under the surface. And to give you a sense of scale, this is a width of about 5 football fields and maybe 1.5 deep. So it's basically like a frozen lake under the surface of Mars. And there's people NASA has contracts with a company called Honeybee Robotics that's developing technology to extract this type of water using the same type of technology that's used in Antarctica to get water ice from, or to get liquid water from the ice in Antarctica using a Rodriguez well. So lots of resources on Mars. The really exciting thing is how we can combine these things together. So we did a study back in 2016 that looked at what our overall return on landed mass would be if we could take the CO2 and the water on Mars and then turn that into liquid oxygen and liquid methane. So the graph here shows how much propellant you would need to leave the surface of Mars. It's about 30,000 kilograms, 30 metric tons of propellant. The blue is just the oxygen. So the majority of any propulsion system is liquid oxygen. It's like 80%. So if you can make the oxygen, you've already made 80% of your propellant. The white bar is the liquid methane. So if we were to put an ISRU plant that's basically the technology that MOXIE uses and just scaled up and only produces oxygen, then we would land the fuel and we would land an ISRU plant in order to make that much oxygen. So huge return on landed mass, save billions of dollars. If we were to also, we would have to land roughly a couple thousand kilograms worth of hardware to produce 30,000 kilograms worth of propellant. So a huge return on investment there. So this is something that we can do. This is actually the reason, or the fact that we can make liquid oxygen and liquid methane on Mars is the reason that SpaceX chose LOX methane for their Starship propulsion system. And this is how all of these things kind of tie together. This is one of my last charts. So one of the nice things about the carbothermal process that I mentioned earlier is that it would use all of the same technology that we would need to make liquid oxygen and liquid methane on Mars. So theoretically, we can start by putting a carbothermal plant on the lunar surface that initially is making oxygen, which would be a benefit in its own. Once we've continued or completed our prospecting campaign for water and we actually can start mining water ice, we can bring the water ice into the same system that already exists and actually start using that hydrogen combined with carbon to make methane. So the only thing we would have to bring is carbon, which is pretty light and easy to store. But by doing that, you get the benefit of not having to liquefy hydrogen. You would only have to liquefy methane, which is a lot easier to deal with. It turns liquid at about the same temperature as liquid oxygen. So that's a benefit. Plus, you'd be able to make your fuel, and you'd be using all the same technology that we'd want on Mars. So this is an architecture that we've been looking into, or at least there's a lot of benefits to this approach. So we're developing all these little pieces now, and hopefully we'll be able to start turning this into real hardware very soon. Some of these aspects are already, ready to fly. So last chart is, I just like to point this out. This is something I get excited about, is all of these technologies. We're talking about making rocket fuel out of water and CO2. These are things we're eventually going to have to use on Earth. As we transition away from fossil fuels, regardless of the politics around global warming and all of that, which, Earth is getting hotter, but aside from that, we're going to run out at some point of fossil fuels. It's a finite resource. So eventually we'll have to figure out ways to produce fuels from the things that we have that are renewable. And there's a lot of examples of companies that we've worked with who are using ISRU technology already. For example, the water electrolysis has been used to make hydrogen at a large scale out in California, where they're pushing the hydrogen economy. There's a company in Texas that's using hydrogen reduction to make steel without carbon emissions. Solar carbothermal process can be used to make silicon with just using solar energy, which we can use for producing solar panels and silicon. The Sabatier process is a way that we can use to make large amounts of methane as well. And actually, SpaceX hasn't advertised much, but they are actually trying to do these things on Earth to fuel Starship using resources here as well. So they're actually trying to terrestrially use ISRU for Starship, which I give them credit for. They don't talk about it much, other than I think one news announcement about that a few years ago. But it's always good to see when we invest in these type of technologies, when you see this terrestrial spinoff. And that is my last slide. So once we learn how to live on the moon and Mars, then we'll be able to take our next steps. And I'll be happy to take any questions.
It's been amazing having you here. I think we can all agree that the beauty of all of this lies on the nature of all this work and the complexity, because I think it's too complex, but it's truly wonderful and amazing. Before we continue, we're going to have a little space for a few questions. So if you may raise your hand to, okay, we have questions here.
Well, first, thank you very much for your presentation. And I was wondering, I saw many equipment to do all the process, especially to extract water, and especially I got wondering, because of the amount of material that we need in order to make a reasonable amount of water, I was wondering, where would we get the power, probably electrical power, to run all the equipment necessary to do the process?
Right. Yeah, excellent question. So ISRU does require a lot of power. So yeah, the question is, well, will we get the power? So, I think primarily there's two main sources, right? There's abundant solar on the moon. So in the architecture studies that we've done, we've looked at a couple of different things, nuclear power and solar power. And nuclear power makes a lot of sense in the permanently shadowed regions where the water is, because that can operate 24/7. And something like a nuclear reactor, or even an RTG that powers the Mars rovers, actually has a lot of waste heat. So just the heat by itself is what we want. We don't necessarily need to convert that into electricity to get the water out. We just need the heat. So even something like an RTG from Mars, which only produces about 100 watts of electrical power, but produces 2 kilowatts of thermal power, if we could pump that energy into the ice, then we can use that to vaporize it. So nuclear works well, I think, for the PSRs. And then we would probably most likely use solar in the sunlit areas to perform the water electrolysis steps, which also require a lot of power, and as well as the liquefaction. But it's not an unreasonable amount we're talking kilowatts of power. So there's a lot of studies out there that are talking about megawatts of power being available on the lunar surface. So there are a couple ways to do it, but but yes, ISRU is going to be very much tied to having large amounts of power as well. So good question.
First of all, thank you for the presentation and your work. I was wondering how possible is to create a hybrid system for extraction using maybe fusion based on thorium or any type of renewable energy for this kind of situation that you mentioned in the presentation.
Okay, let me make sure I understand the question. Beneficiation of, did you say thorium?
Using like a hybrid system, using similar that we're using in cars here in Earth, that is electric and gas propulsed, but using well, like a similar system, but using nuclear energy for that type of.
Okay.
For like some kind of assistance.
Right. Okay. So hybrid power. I think so. One of the technologies that has been used terrestrially that is somewhat competitive to hybrids is they do have fuel cell vehicles now. I think that is the most likely form of mobile power that we'll be using on the lunar surface. So, for example, I know currently JAXA is developing a pressurized rover, and we have a team at JSC that'll be developing a fuel cell for that rover. So the fuel cell runs off of hydrogen and oxygen, which of course is another use for water. So you don't necessarily have to liquefy those products for them to be useful. You can use them to power a fuel cell on something like a vehicle or even just for lunar night survival. Good question. Thanks.
Well, I'm sorry, that's all the time we have today. I know we will want to hear more and more and more. I'm going to ask you to please reach to him later. But right now, on behalf of the organizing committee of this our special forum, I want to say thank you. And we are truly grateful for your presence here, for your experience, for your time, for all of this that you're sharing with us right now. And we want to give you a present as a symbol of gratitude.